Okay, today in IM2 we're going to talk about quadratic relations and functions when we add c. So we know that the standard form of a quadratic equation is of a function is ax squared plus bx plus c. Yesterday we talked about this part of the function and what happens when we do have just a which is positive, negative, or a number. And today we're going to add c. So how do you think c would affect the graph? We know that a can flip it upside down, it can stretch it out or shrink it up. What does c do? So let's compare some graphs. So we have this basic function right here, and then we look at the basic function plus 2. Tell me what happened to the function. Look at the vertex, okay? And then over here we have a basic function of 2x squared, and all they did here was add a c of minus 2 and it dropped it down. So if you were describing this effect as a translation, how would you describe it? Okay, so it's a vertical translation. When it's plus, it's up 2, and when it's down, when it's negative, it's down 2. So describe how the graph of each of these functions would be different from the basic function. Don't graph them, just look at it. Okay, now see how you did. So if you look at 2a, it's the same as the basic function, but it's moved down 7. Okay, and so be careful with this one because we also have a negative here. So we know that it's a reflection over the x-axis and up 1. They usually do the reflection first because it's kind of hard to remember to do both, so it's easier to do the reflection first. Just trust me on that. Try it a couple times. Okay, so this is just an explanation in your book. It's also in your journal, so you can look at that for an explanation of what c does to your graph. So if we're going to compare the quadratic function, this quadratic function, to y equals x squared, what is happening? Okay, if we were going to graph it all, we would figure it all out, and we would see that it went up 2. Okay, now look at this one. We have 3 things happening. Don't forget to take into account all 3 things. Okay? So what happened here? Okay, so I'm going to show you the picture, and we're going to describe it. So it's a reflection over the x-axis. It's a vertical stretch by a factor of 3, and it went up 1. So notice these 2 things usually get done. I would just graph it and then describe it, but you can also just describe it by looking at the graph, the equation I mean. Okay. An important thing to remember about quadratics is the 0 tells you how many times there are x, or how many x-intercepts there are, okay? Because the 0 is an x-intercept, is also a solution. There's lots of names for it. They also call them roots. So depending on the book or the program that you go to, they will call them different things. So the zeros are how many times. So if you look at this, a quadratic can have 1 0, which means that it's going to hit it once. We can go from the top or the bottom, and that is a perfect square trinomial. They only have 1 0. Because remember, it would be like x plus 2 squared. So negative 2 would be my 0. Okay? All right, if you have 2, it's just a regular parabola that goes like this or like this. You can see there's 2 zeros. Okay? Or no zeros, meaning it never touches the x-axis. Okay? So it's important that you understand those differences. Okay, so find the zeros of this quadratic function from its graph. So it's not hard to do. The zeros are right here, And if we factored, we would find them because those are the solutions of our graph. So if we go -3, -2, we have -3 and 1. So x minus 3, x plus 1. Those are my factors. My solutions are 3 and -1. And sure enough, those are my factors, my zeros, my solutions, not my factors. These are my factors. These are my roots, my solutions, my x-intercepts, and my zeros. So you try this one. Okay, if I was going to factor this, it would be x plus 4 squared. It's a perfect square trinomial. -4 is my one root. And then this one, I do not have a zero because it is not touching the x-axis. Okay, so how would you check your answers? This is a fun thing. So when you get the answer, x equals -4, if you plug that number in here, -4 squared plus 8 times -4 plus 16, it will equal 0. So I get 16 minus 32 plus 16, and that equals 0. So it does work. And there you go. So your zeros tell you when it equals 0. Because look, y at this point is 0. So this is -4, 0. This is 3, 0. This is -1, 0. So that's how you check your answer. Okay, a vertical motion model, we've talked about this a few times, is a quadratic equation that models the height of an object at a given time. The equation is of this form. So, the g of t represents the height of the object in feet at any given time. The t represents the time in seconds that the object has been moving. The v is the velocity, the initial velocity when it's thrown or whatever. There is no velocity if it's just dropped. You'll see examples like that in your homework. And h is the initial height of the object in feet. So this is where it starts. So those are important things to remember. Okay, so how would the graph change? So this is just something being thrown and coming back down. So it's going to a height of 400 feet, so it must be being hit with a baseball or something. And then it's landing back down. My zeros are 0. It started at 0 seconds, and it landed at 10 seconds. So it was in the air for 10 seconds. So what if it was thrown off a 600-foot building? Then it's going to look like this. Now this is if it's thrown off. Okay, if it's dropped off, it's going to look more like that. Okay, there's a difference. Thrown off implies it's being thrown up and down, but dropped is just dropped. All of these have the shape because time is passing. Okay, if it was hit from a hill, then it might go up even higher and come down. Okay, so there's a lot of different ways to see the graph. So I thought this one was really good because it explains how they came up with the perpetual motion model. So this represents the distance in feet of a dropped object that a dropped object falls in t seconds. Okay, so then it says SO represents the initial height. Remember, that's our C, and in this case it's 64. So they want you to find and interpret the h of t when you have this function. So you're going to take this function and put a negative in front of it, and then you're going to add the S of O, which is the initial height of 64. Okay, so that's what they're trying to teach you from this perpetual motion model, and then you're going to answer these two questions in a bit. So I'm going to put their explanation up here, showing you how to come up with the perpetual motion model, and that explains it a little bit better, so you can stop and look at that if you want. This is also in your book. Okay, so now we're going to discuss the problem in a little bit more depth. So the egg is dropped from a height of 64 feet. So we're going to replace that SO with this. So the initial height 64, so now we have an equation. They want to know after how many seconds does the egg hit the ground. So they're saying that y equals 0. So we're going to factor this we're going to factor out a negative 16, and we get t squared minus 4. Okay, that means we get negative 16, t plus 2, and t minus 2. So right away we know that this one, the negative 2, represents the time before the graph, and we're just going to, and so positive 2 is how long it's going to take it to hit the ground. So if you look at this negative 2 represents the mathematical model of negative 2. Okay, but we don't use that. We only need the positive time, and you can see that it's 2. Okay, now this is the interesting part, and they're trying to teach you how it is affected by c, by adding a c. So now they're saying that the initial height is adjusted by k feet. So it's either going up k feet or down k feet. And they want to know how that's going to affect your answer here. Okay, so logically, if we're going to go up, it's going to take longer for it to hit the ground. If we go down, it's going to take less time. And that's what they want you to come up with. So when k is greater than 0, if you're going up, the egg's going to take more than 2 seconds. If k goes down, if k is negative, then the egg is going to take less than 2 seconds to hit the ground. So that's a really good example to show you how you would use the adding or adjusting of c to change the answer to your problem. Obviously, throwing eggs off a building isn't really serious, but it is important that you understand the concept. Okay, so let's look at this problem in our journal. So it says the f of t equals 16t squared plus the s of o represents the approximate height in feet of a falling object t seconds after it's dropped from an initial height. So they're dropping the tennis ball. It's falling from a height of 400 feet. That's why there's no b. It's not being kicked or thrown. It's just dropping. So we're going to set up our equation. The f of t equals negative 16t squared plus 400. And they want to know when is it going to hit the ground. So starting at 400. Okay. And so this is the real part of our graph, right? And so we want to find out this answer. So I'm going to factor negative 16, and I'm left with t squared minus 25. So I'm going to factor that. That's negative 16 t plus 5 and t minus 5 because it's a difference of two squares. So I have negative 5 and positive 5. Obviously, the only one that counts is the 5 seconds it took for the tennis ball to fall from 400 feet down to the ground. So then it says, well, suppose the initial height is decreased by 384. So they're telling you to take 400, subtract 384, and you get 16. So now my equation, let's call it the g of t, equals negative 16 t squared plus 16, because that's my new starting height. I'm going to factor out negative 16. I get t squared minus 1. Remember that this is still a difference of two squares, so it's negative 16 t plus 1, whoops, that's a 1, and t minus 1. So this is negative 1, which represents the part of our graph that we can't see because it's mathematically impossible, or it's mathematical, but it's not possible in the real world. So 1 second. So it's going to take 1 second for our ball to fall from a height of 16 feet. So I hope that helped you understand it a little bit better. Okay, so without graphing, this is just some simple point, but there's problems like this on your homework. Tell whether each point is on the graph. So all you do, this is your x, y, and you plug that in. 16 equals 1/2 times 4 squared plus 8. And you're asking, does it equal 1/2 times 16 plus 8 is 8 plus 8, and it works. So it is a solution of your graph. Okay, let's try a couple more of those. So we're going to plug in 0 equals 1/2 times negative 4 squared plus 8 is 1/2 of 16 plus 8, and 8, whoops, not 18, and 8 plus 8 does not equal 0, so that is not a point on your graph. Okay? Try another one. This one's a little bit more difficult. So the first thing you want to do is look at the graph carefully. I'm going to put it into standard form. Okay? So now I see that its y is 10.5, and I'm going to go negative 3.5 squared plus 2. Remember, it only replaces this part. So the negative is still there, which means it's probably not going to work, because if we have a negative number there, it's not going to equal 10.5. So we're going to get negative 12.25 plus 2, which is definitely not going to equal 10.5. Okay, and let's try one more. So we're going to plug in 1. So this one's really easy, so you could just go 1 plus 1 equals 2, and that works. So this one is a solution, and now you're ready to do your homework. Ta-da!